class. Today we're going to be talking about inverse functions. The first thing that I want to have you notice is function notation. So when you were in Algebra 1 and probably pre-algebra, you typically saw equations written like this. Y is equal to, and it might be, say, 3x plus 5. Or you might see y is equal to 2x, or, something like that. And that's perfectly fine notation. But then as you move into higher math, you typically need to write things in function notation, which is f of x is equal, and then whatever the function is. Inverse notation is a little bit odd looking. See that raised? It looks like an exponent of -1 because it's raised. It doesn't actually act as an exponent, but it is notation. It's f with that superscript, -1 of x is equal. And what functions do is they undo each other. So I'll give you an example of something you're familiar with. Addition and subtraction undo each other. Multiplication and, wait for it, yeah, you got it, division undo each other. Exponents, exponentials, exponent, I should put, and logarithms. All of these things undo each other. Okay, so let's go ahead and take a look. So one of the ways that you can determine if a function and its inverse are actually inverses of each other is if you graph them. So if you go to Desmos and you were to type in both of those what look like functions, y is equal to 2x plus 5, and then you would also type in y is equal to x subtract 5 divided by 2, you get these two graphs right here. So here is this second one right here, and here's that the original function, and I kind of put it in gray, kind of gray highlighting, but they are reflected over each other, right? So, and we're going to look at this f of x equals x cubed, which is the function starting here and it ends right here. Well, actually they go on and on forever, but you know what I mean. The orange line is the original function, and the inverse function, f with the superscript -1 of x is equal to the cube root of x. And notice again, this kind of invisible asymptote right there, and the graphs are reflected over each other. That's how we know function what look like could be their inverses are actually true, is their graphs will be reflected over a plane, and they'll look like they belong together. Okay, the other thing that I don't think I remember to cover with you guys, and I need to do that really quickly, is also there's one quick way for you to know if a function even has an inverse, and it's the horizontal line test, not a vertical. Vertical line test tells you if it's a function. A horizontal line test, let's see if I can get this line very straight, very horizontal without it. So the horizontal line test is I'm going to bring this out a little bit more. You put it through the function all the way down, and if it only touches in one spot, then this function right here does have an inverse. So let's go over here to a quadratic, a parabola. Notice during the horizontal line test, it crosses that parabola in two places. So this graph would not have, this function would not have an inverse. So that's how you determine graphically, before you even solve inverses, if you were to graph a function first and do the horizontal line test, you'd know right away whether or not it has an inverse. So notice here, all the way down, this function right here, this equation only touches the horizontal line in one place. So let's look at the absolute value. Up, does not have an inverse. Now, in the last, when we were talking about vertical line tests, this function didn't pass. This is not a function, so we don't have to worry about inverse, so sorry about that. And the horizontal line is a function, but notice it is not, that is not very straight. It touches it infinitely in infinitely many places. So it does not have an inverse. So there you have it. All right, so now we're going to go back to where we were. And talk about inverses. All right. And just visually how you determine and the horizontal line test. So let's see what you'll be doing for your exercise today. So what you're going to be doing today in class is, I already have answers on here. I have the graphs of these two things. So before we've even solved for inverses yet, here is the original function, here is the inverse, and here is the graph. And so imagine it where they intersect. Imagine perhaps a diagonal line. And are those two lines being reflected through the x is equal to y right there? And if that's the case, then, well, you can tell they have a function. Now this case is very interesting. Notice the original function is -n subtract 4, and look at its inverse. Its inverse is the same. Well, think about that. If you somehow were to graph the asymptote it is still, both lines are reflected over each other. All right, so what I want you to do today is I want you to pay attention to the original function, the actual parts, and then look at what the inverse looks like, and then pay attention to the graphs. And if you want to mess around with it, go to Desmos, and in Desmos type in a function and hit enter, then type in the inverse function so you can start playing around with the graphs a little bit. All right, so we're gonna, and you're just going to keep doing that. So these are linear functions, and these are polynomial functions. There's polynomial function to the 5th degree. There's a 5th root, cube root, and just get really comfortable with what the graphs will look like. You'll be doing some of that. And then here are some rational functions and what their inverses will look like. All right, that's it. That's what we'll be doing today.